In this video, we learn how to identify valence electrons in atoms. That is, the electrons that are explicitly involved in bonding. And we show how the structure of the periodic table is not only linked to electron configurations, but more specifically to the valence shell electron configurations. In previous videos, we saw that we could write down the electron configuration for any element on the periodic table by using the Aufbau principle or by using the periodic table itself as a guide. And we specifically determined the full electron configuration of lead, shown here. We also know that we can write the condensed electron configuration by identifying the electron configuration of the noble gas immediately preceding lead in the periodic table, which in this case is xenon, and put the xenon symbol in the square brackets followed by the rest of the electron configuration. These electrons here representing the electron configuration for xenon are called the inner shell or core electrons, and these electrons take no part in chemical bonding. The inner or core electrons consist of full shells and full subshells, and as such are stable, and therefore they are not disturbed or changed when atoms bond with each other. The remaining part of the electron configuration correspond to what we call the outer shell electrons. Now it turns out that subshell designations in electron configurations can be written in two ways, or using two different orders of subshell designation. The first involves writing the subshell designations in order of increasing energy, and this is the way we have represented it here at the moment. The second way involves grouping subshells according to the value of n, or in other words, grouping subshells within the same shell together. So, for example, we can see that the two electrons in the 1s subshell belong to the n equals 1 shell, and we can see that the electrons in the 2s and 2p subshells belong to the n equals 2 shell. Electrons in the 3s and 3p subshells belong to the n equals 3 shell, and then we get to electrons in the 4s subshell, which is the next highest energy subshell that, correctly, needs to be filled. But we can see here that we still have 3d electrons that belong to the n equals 3 shell. And it may be that we would want to group all of the n equals 3 subshells together. And similarly, we might want to group all of the subshells at the n equals 4 level together. And we might want to group all of the subshells at the n equals 5 level together. And we might want to group all of the subshells at the n equals 6 level together. So if we were to do that, the electron configuration would look like this, where we start with the single n equals 1 subshell, and then all of the n equals 2 subshells are grouped together, and then all of the n equals 3 subshells are grouped together, and then all of the n equals 4 subshells are grouped together, and then all of the n equals 5 subshells are grouped together, and finally all of the n equals 6 subshells are grouped together. This gives us two ways of writing the condensed electron configuration. This way, corresponding to the electron configuration on the top, or this way, corresponding to the electron configuration on the bottom. In this one, the subshells are written in order of increasing energy. In this one, subshells within the same shell having the same n value have been grouped together. Now, either way of representing the electron configurations are valid, but I want to focus on this particular way where the subshells within the same shell are grouped together. And this is convenient because it allows us to easily separate the outer shell electrons that are unavailable for bonding from those outer shell electrons that are available for bonding. As we have already noted, these electrons associated with the xenon core are called the inner shell or core electrons, and they are not available for bonding. These electrons are called the outer shell electrons, and it turns out that only some of these are available for bonding. This part of the outer shell electron configuration, the 4f14 and the 5d10 electrons, represent electrons in full subshells, and we know that full subshells are stable. So these electrons are not available for bonding. The electrons in this part of the outer shell configuration belong to the shell with the highest n value, in this case n equals 6 for the lead atom. These are the electrons that are available for bonding. These are the valence electrons, the subset of the outer shell electrons that belong to the highest n value. This is a table that shows condensed electron configurations for main group elements, that is, elements that appear in the S and P blocks of the periodic table. What is evident here is that the electron configurations are not only related to the overall structure of the periodic table, but closely related to the specific position of an element within the periodic table. We can see that the periodic table is structured so that elements in the same group have the same pattern of valence electron configuration. For example, all group 1 elements have the NS1 valence shell configuration, meaning they have a total of 1 valence electron available for bonding. All group 2 elements have the ns2 valence electron configuration, meaning they have a total of 2 valence electrons available for bonding. Group 13 elements have 2 s electrons and a single p electron available for bonding. Group 15 elements have 2 s electrons and 3 p electrons available for bonding. Group 16 elements have 2 s electrons and 4 p electrons available for bonding. And group 18 elements have 2 s electrons and 6 p electrons available for bonding. But we know that these electron configurations represent full shells and full subshells, giving stable electron configuration, and therefore these elements tend to resist forming chemical bonds and being involved in chemical reactions. Originally, the periodic table was structured so that elements with the same or similar chemical and physical properties were placed in vertical columns, known as groups. We can now see that the modern version of the periodic table is arranged such that outer shell valence electron configurations are arranged in vertical columns, and the similarity in chemical and physical properties is actually the result of similar valence electron configurations. For example, it is not surprising that lithium, sodium, potassium, etc. all share the properties of being soft, lustrous, highly reactive metals that produce hydrogen gas when reacted with water. This is because they all share similar valence electron configurations with a single s electron available for bonding. Similarly, for the noble gases, which are all stable, monatomic, non-reactive gases, the electron configurations all have completely full shells and subshells, which is responsible for the stability and non-reactive nature of these gases. It is important we get our language correct here. Valence electrons are those electrons that have the potential to be involved in chemical bonding. Valence electrons include either all outer shell electrons or a subset of the outer shell electrons that belong to the highest occupied n value. For elements with an atomic number less than 30, all outer shell electrons are considered valence electrons. For heavier elements, electrons in completely full subshells are not considered valence electrons. Going back to this table, we can see that these electrons that occupy full subshells are not considered as valence electrons or bonding electrons. However, the rest of the outer shell electrons in these condensed electron configurations would be considered as valence electrons. Staying with this table, the importance and significance of the old Roman numeral naming convention for groups becomes apparent. For example, all group 1A elements have 1 electron available for bonding, or 1 valence electron. All group 2A elements have 2 electrons available for bonding, or 2 valence electrons. All group 3A elements have 3 electrons available for bonding, or 3 valence electrons. All group 5A elements have 5 electrons available for bonding. All group 6A elements have 6 electrons available for bonding. And technically, all group 8A elements, with the exception of helium, have 8 valence electrons available for bonding, although as we know, these are very stable electron arrangements, and only the heavier group 8 noble gases tend to form bonds with other atoms, and even then very rarely. By using the old convention for naming of groups, for example 3A, 4A, 5A, etc., we see that the total number of valence electrons available for bonding is equal to the Roman numeral group number. And this becomes important when we consider bonding theories a little later.